Lab 5 was about BJT transistor characteristics and amplifiers. This presentation will cover the objectives of the lab, the theoretical circuit analysis, where we sketched the current voltage characteristics of a BJT, and designed two common emitter amplifiers. In the theoretical analysis, we solved for capacitor and resistance values for these amplifiers. After the theoretical portion of the lab, we created CAD simulations through LT-SPICE to verify the theoretical calculations. We then applied the previous two steps of the lab in the experimental section, where we reproduced our theoretical and simulation values. We will conclude this presentation with the results from each section and conclusion. The lab objective was to verify the current voltage characteristics of our BJT transistors, bias them, and design single-stage transistor amplifiers. The theoretical analysis requirements wanted us to sketch the current voltage characteristics of BJT transistors for a particular set of model parameters, design a common emitter amplifier to provide a small signal gain of -10, and design a common emitter amplifier with variable adjustable gain. The first part of the theoretical analysis was to sketch the current voltage characteristics of a BJT transistor for a particular set of model of parameters. Figure 1 shows that there will be a little to no current until the voltage between the base and the emitter is approximately 0.7 volts. After this point, a small change in voltage creates a large change in current. Figure 2 shows that the current is dependent on the difference in the collector and the emitter voltage until the voltage exceeds between 0.2 and 0.3 volts. After 0.3 volts, the collector current is no longer dependent on the voltage difference. The three lines indicate the different values of VBE, which is the voltage difference between the base and emitter. In both of these figures, IE is approximately equal to IC. Requirement 2 of the theoretical analysis asks us to design a common emitter amplifier to provide a small signal gain of -10 using a single power supply of 15 volts. Using a biasing network robust to beta variation to provide a quiescent collector current of 1 milliamp, we were asked to choose the value of the collector resistor to maximize the output swing. Figure 3 is a sketch of the common emitter amplifier we were asked to design. After sketching the circuit, we needed to solve for RC, RE, and the bias network resistors. We started by solving for RC. We wanted to maximize the output swing, therefore the output needed to be centered around 7.5 volts. This means VC should equal 7.5 volts. Using Ohm's law and the design quiescent current of 1 milliamp, a 7500 ohm resistor was chosen for RC. This is shown by figure 4. After finding RC, we used the gain equation to choose RE to produce a gain of -10. RE equaled 750 ohms, and this is shown in figure 5. R2 can range from equaling RE up to 10 times RE's value. To create the most robust circuit, independent of temperature variation, we chose R2 as 7500 ohms, and this is shown in figure 5. To find R1, we found the voltage at the base using the quiescent current at RE and adding 0.7 to account for the additional voltage required for the BJT. Then we used a voltage divider to calculate R1. All of this is shown in figure 7. The input and output voltage are coupled with capacitors to isolate the circuit. These are calculated using the equation provided in figure 8. We selected a frequency of 1000 Hz and determined the equivalent resistance for each capacitor. To calculate the capacitance of capacitor 1, we looked into the system where we could see that R1 is in parallel with R2, which is also in parallel with the emitter resistance. The emitter resistance is small RE, the resistance in the BJT, in series with the emitter resistor. To find the value of capacitor 2, we looked into the system from capacitor 2 and saw that the only resistance is RC, which is 7.5K. The third requirement in the theoretical analysis was to design a common emitter amplifier with variable adjustable gain, using a potentiometer in parallel with emitter resistance coupled with a capacitor. The same circuit was used, but there was no degrees of freedom to control the gain. A resistor was placed in parallel with the emitter resistor, coupled with a capacitor. The new capacitor was calculated using an equivalent resistance of Rg in series with Re. The capacitor at the input was also resized to account for the new emitter resistance.